In today's lesson, we are going to cover integrals with the natural log function and e. Previously to this, we had written down what the integral rules were, but today we're actually going to practice doing integrals with them. So here's our first two examples. Neither of these look like something that maybe is easy to rewrite. And that's something I'd always want you to try first, is if you're able to rewrite it in a way that we're able to use one of our simple integration formulas, then I would prefer you do that. However, with both of these, we can't really rewrite them in a way that we can use the reverse power rule or any of the other rules that we've learned for that matter. So when that happens and you're not really sure how to rewrite it, or you don't think it's possible to rewrite it in a way that's easy to take the integral of, then I would say go and think of u substitution. So what can we make u equal to? And again, typically with u substitution, we look for things like that are grouping things together. So for example, if you have parentheses, which I don't see in either of these, if we have a radical, maybe that would be a grouping symbol, but we don't have that either in these problems. Another thing you can look for that's grouping symbols would be fractions, which we do have in both of these. And typically the top of a fraction is grouped together and the bottom of the fraction is grouped together. And so looking to replace one of those with the u is probably where we want to go to next, and the strategy that we would like to use. In this first example on the left-hand side, there's not much to make u equal to on the top, so probably not going to look to that one. Instead, we'll look to the bottom and set u equal to 5x minus 2. So let me go ahead and do that now. U equals 5x minus 2. The derivative of that du is equal to 5 dx. I don't need that extra 5 in there, so I'm going to get rid of it by moving it over to the other side. 1/5 du is equal to dx. If I can start to highlight some of the things that I'm able to eliminate, the 5x minus 2 will be replaced by u, and the dx will be replaced by 1/5 du. That 1/5 is a constant multiple, so I'm just going to pull it out front. That's 1/5 times the integral of 1 over u du. Now remember that we said in the lesson that we did write down the integration rules. It's tempting to look at this and think that it's a reverse power rule and rewrite that as u to the negative 1 exponent. But remember, if you do the integral with that, the integral of u to the negative 1, if you bump up that exponent by 1, would be u to the 0 over 0, and that doesn't make sense. And so this is the one fraction or the one property that doesn't work with the reverse power rule. So instead, the integral of 1 over u or 1 over x is just ln of x, or in this case, ln of u. So this is 1/5 times ln of the absolute value of u plus c. Now the reason we have to put that it's the absolute value is because of the domain of the natural log. We're not allowed to plug anything that's negative or 0 for that matter, into the natural logarithm. So we have to throw absolute value bars around it. And last but not least, if I replace u with what it equals, I get 1/5 times ln of the absolute value of 5x minus 2 plus c. Final answer. For the second one, again, let's look for grouping symbols. In this case, the bottom of the fraction is a nice grouping symbol, so we'll say that u is equal to x squared minus 4. Therefore, du is equal to 2x dx. I don't need that 2 in there, so I'm going to pull it over to the other side. 1/2 du is equal to x dx. If I start to highlight some of the things I'm able to substitute, x squared minus 4 is going to be substituted with a u, and then x dx is going to be substituted with a 1/2 du. Now notice we have that extra 7 in the problem that we don't need either, and it's not taken care of by any of our substitutions. So to get rid of this 7, similarly to what we're going to do with the 1/2, I'm just going to write it in front of the integral. Because 7 is a constant multiple, I can do the same thing with that. So I can just write the 7 in front since I'm multiplying it anyway. So I'm going to write 7 over 2, and that 7 over 2 came from this 7 along with this 1/2. So the 7 times 1/2 in the front of the integral will just be 7/2. And this is the integral of 1 over u du. The integral of 1 over u is ln, so this is 7/2, times ln of the absolute value of u plus c. If I replace u with what it equals, I get 7/2 times the natural log of x squared minus 4 plus c. Final answer. In this example, we're still working with fractions. I could do the bottom of the fraction again like I've been working with in the last example, but walk through it with me before we actually go ahead and write that down. If I make my u equal to x, the derivative of x is just 1, and that does not help me to get rid of this ln of x. So I don't think using the bottom of the fraction in this case is probably the best bet. Instead, let's look for other grouping symbols. So I do have parentheses in this case. Let's see what happens if I make u equal to ln of x. If I make u equal to ln of x, du is equal to 1 over x dx. And that is something I do have. It might not be apparent to you, but let me go ahead and do some highlighting and see if it makes sense. This ln of x is going to be replaced with a u. The dx, and then 1 over x is being replaced with this. So notice that the dx and dx here would be replaced with each other. And then the 1 over x, because this x is in the denominator of a fraction, this is the same thing as 1 over x. So this is 1 over x dx being replaced with du. So if I rewrite this, I have the integral of u to the 4th power du. U to the 4th power is the reverse power rule, so that's u to the 5th power over 5 plus c. And if I replace u with what it equals, that would be ln of x to the 5th power over 5 plus c. With this next example, this is another example of u substitution with a natural log function. The only difference is that now we have limits of integration. So let's go back and practice changing our limits of integration again. So if I set u equal to what's in the bottom of the fraction, like we did in those first couple examples, u would be 2x plus 1, du would be 2 dx. I don't need that 2, so I'm going to pull it over to the other side. 1/2 du equals dx. So dx is going to be substituted with a 1/2 du. 2x plus 1 is going to be substituted with a u. Notice I have this extra 4 in here that I don't need, so I'm going to pull that out front. And so if I pull this 4 out front and the 1/2 is out front, then this 4 times this 1/2 that would be out front would be 4 times 1/2, which is 2. So this is 2 times the integral of 1 over u du. And then for my limits of integration, if I change those, when x is equal to 0, that lower limit of integration, u is equal to 2 times 0 plus 1, which is 1. When x is equal to 4, the upper limit of integration, u is equal to 2 times 4, which is 8, plus 1, which is 9. So my new limits of integration are from 1 to 9. If I do this integral, I get 2 times the natural log of the absolute value of u. And then remember, we don't need the plus c if we're doing definite integration because it's going to go away anyway. The limits of integration are from 1 to 9. So this is 2 ln of 9 minus 2 ln of 1. And hopefully you remember that ln of 1 is equal to 0. So this is just 2 ln of 9. Final answer. All right, here's some more that have definite integration as part of them. Now be careful with this first one in terms of what you're going to make your u equal to. If I make u equal to the entire denominator of the fraction x ln of x, then I have to use the product rule when I take the derivative. And the product rule for that is a little intense, and I don't think it's going to help me eliminate anything else in my fraction. So in this case, I actually probably do not want to use the entire denominator for my u substitution. Instead, we could just choose pieces of it. So if I just chose an x, that's probably not very helpful because the derivative of x is just 1. That doesn't help me get rid of ln of x. If I choose ln of x for my u, the derivative of that would be 1 over x, which does actually help me get rid of this. So that would be actually kind of helpful. Let's try that. So if I make u equal to ln of x, du would be 1 over x dx. If I do some highlighting to show you what gets eliminated or substituted, ln of x will be replaced with ln of x. And then 1 over x dx will be replaced with 1 over x dx. So this is now the integral of 1 over u du. For my limits of integration, my lower limit is x equals e. Therefore, u is equal to ln of e, and ln of e is equal to 1. And for my upper limit of integration, if x is equal to e squared, that means u would be equal to ln of e squared, which is 2. So my limits of integration are from 1 to 2. If we go ahead and actually perform this integral now, the integral of 1 over u is the natural log of u, natural log of the absolute value of u. Again, I don't need my plus c since I'm doing definite integration. My limits of integration are from 1 to 2. If I use the fundamental theorem of calculus, that would be ln of the absolute value of 2 minus ln of the absolute value of 1, and ln of 1 is equal to 0. So this is just ln of 2. For this next example, again, let's decide what we want our u to be. If I make my u equal to the top of the fraction, which is sine of x, the derivative of sine of x is cosine of x, which would help me get rid of the cosine of x, kind of, except for the fact that the cosine is in the denominator, and the derivative of sine doesn't go down to the denominator, so that would be a problem. If I make my u equal to the bottom of the fraction, 1 plus cosine of x, I think that would be the best bet. U equals 1 plus cosine of x. You could, by the way, make it equal to just cosine of x, but the more you're able to grab with your u, the better. So if you're able to grab constants in there and the constants won't affect your derivative, that's probably the best thing to do, is to grab all of that into your u so that when you take its derivative, it becomes the simplest problem possible to be able to solve. So du, the derivative, would be equal to negative sine of x dx. We need that sine of x, we need that dx, we just don't need the negative, so I'm going to move it over to the other side. Negative du is equal to sine of x dx. If I do some highlighting to show you what gets taken away, the 1 plus cosine of x goes away, and sine of x dx gets replaced by negative du. So this becomes the negative integral of 1 over u du. My limits of integration, my lower limit is x equals 0. For u, that would be 1 plus cosine of 0. Cosine of 0 is equal to 1, so that would be 1 plus 1, which is 2. For my upper limit of integration, x equals pi over 2. U would be 1 plus cosine of pi over 2, and cosine of pi over 2 is equal to 0, so that would be 1 plus 0, which is 1. So my limits of integration are from 2 to 1. And again, that's backwards. We could fix it right now if we wanted to. We could flip it upside down and make this the integral from 1 to 2 and have it be positive, but I'm just going to leave it like this, since my fundamental theorem of calculus will take care of that for me anyway. The integral of 1 over u is the natural log, so this is negative ln of the absolute value of u, and my limits of integration are from 2 to 1. If I use the fundamental theorem of calculus, this is negative ln of 1 minus a negative ln of 2. Well, ln of 1 is 0, so this is 0 minus a negative, which turns into 0 plus ln of 2. So it's just ln of 2. So same answer as the last problem in the sense of... Same answer as the last problem in the sense of the area under the curve. Sorry, my dogs are going crazy over here. But different problem altogether. They just happen to have the same area. All right, for these ones, these are examples of the integral with e. So notice we have a bunch of e's in here now. For the first one, I'm going to make my u substitution equal to the exponent on e. So typically we'll always do that, where we make u equal to whatever's in the exponent of e. Just like when we were doing the chain rule, we would always make the inside what was equal to the exponent of e. So we're going to do the same thing here typically. So u is equal to 1 minus x. Du would be equal to negative 1 dx. I don't need that negative, so I'm going to move it over. Negative du is equal to dx. I don't need this 4 either, so when I rewrite this, let me do some highlighting so you guys can see this. The 1 minus, oops, that's not a highlighter. The 1 minus x is going to be replaced with u. The dx is going to be replaced with negative du. This extra 4, however, I don't need, and so if I don't need that extra 4, I'm just going to pull it out front, since it's a constant multiple, and it will sit out there with that negative. So if I rewrite this, I get negative 4 integral of e to the u du. Well, the integral of e to the u is itself, so this is negative 4 e to the u plus c. And then if I replace the u with what it equals, that's negative 4 e to the 1 minus x plus c. For the next one, again, let's make our u equal to the exponent, so u equals x squared. Du would then be 2x dx. Notice that I actually do need all those pieces. Here's my x squared that's going to be replaced with u. Here's my 2x dx, which will be replaced with 2x dx du. So if I rewrite this, I have the integral of u du. Oh, sorry. E to the u du. Integral of e to the u is itself, so this is e to the u plus c. If I replace u with what it equals, that's e to the x squared plus c. And as always, as we've mentioned before, if you need a little convincing on where certain things come from, make sure you try to take the derivatives once you get to the final answer. Try to take the derivative and go back to the beginning again. See if it makes sense to you. All right, this is our last example for this lesson. Our u in this case. So we said typically we would make u equal to the exponent on e, but in this case the exponent of e is just x. So again, that doesn't lead us to very much help to make u equal to a single variable. So instead, let's go back to looking for parentheses, which I don't see any radicals, but I do see this fraction idea. If we make u equal to the top of the fraction, e to the x, its derivative is just itself, e to the x, so that doesn't really help me to eliminate this bottom. So instead, I'm going to make the denominator equal to u, 4 minus e to the x. du would be equal to negative e to the x, dx. I don't need that negative, so I'm going to move it over to the other side. Negative du equals e to the x dx. And that helps me get rid of all these pieces. So 4 minus e to the x is replaced with u, and e to the x dx gets replaced with negative du. So this becomes negative integral of 1 over u du. Integral of 1 over u is ln, so this is the negative natural log of u plus c. If I replace u with what it equals, that would be negative ln of the absolute value of 4 minus e to the x plus c. Final answer. All right, that's it for the notes for today.